on the other side. So these are really going to be like some kind of categories of modules. And the only thing that I really want you to get out of it is that one, I've got one of these on each side. And then second, that these things are going to be some categories that are of interest in geometric, in representation theory. Even without any sort of physics. These things, so I'm going to describe maybe an example of one of these categories that you might have seen before in a little bit, and try and convince you that it's a category that's interesting and that you like it. And then this mirror symmetry is supposed to be some kind of, or the symplectic duality is supposed to be some kind of equivalence of these two things. So this is the symplectic duality. And then I just want to say a couple more words, and then I'm going to kind of leave this picture behind and talk about something a little bit more concrete. So just at least for the history of the subject, this side is relatively well understood. If I had more colors, I would be even more happy. So this side is well understood. It's mathematically well defined. So at least, like, I could give you a definition of this variety, and it would be in terms of something that that is extremely old. But roughly until last year, this had no definition. That a mathematician could understand. Like basically you could compute some sort of an approximation to this variety, but like that you would need to do some sort of like Feynman diagram calculation, and it would have some infinite series of corrections to the metric, and nobody knew like how to figure out what that did, and so nobody knew what on earth this space even was. And so without having a good definition of this space, it's hard to have a good definition of this category, and this is sort of a hard thing to prove. But there are sort of a lot of examples where people actually like had some idea of what the answer should be ahead of time, even if they didn't know how to calculate it in some rigorous way from this picture. And you know, people were still able to make some progress in comparing these sides. So maybe like my talks in a few days is maybe I'll start to talk about what exactly this definition is. Okay, so this is sort of like the game plan for sort of, by the time that I'm done, I want to kind of explain all of this. For today, all I'm going to try and explain is what do I mean by a symplectic cone, like what kind of a variety is this, and then how does one define this category given a symplectic cone. And then we'll come back to sort of this more general picture at some other. Okay, so sorry, that was extremely vague, but now I'll be able to get a little bit more, get a little bit more precise and concrete. Okay, so I want to talk maybe for a minute about like the mathematical prehistory of this subject. And so that means I want to talk about things, well, from the 1950s, which I think people would agree was prehistory. The 1980s, maybe a little bit less so for some people. And then you can tell that I'm a young person when I think that the 90s was such a long time ago. And so sort of the mathematical prehistory is going to be a bunch of outgrowths of a bunch of theorems of Borel, Bay, Bott, Beilinson, Bernstein, and then Beilinstein, Ginsburg, and Sorgel. So I want to try and explain like what these theorems are, and then how they were sort of generalized. So let G be some semi-simple group over C, and then let G be its Lie algebra. And then I'm going to fix a torus sitting inside, and then a Borel containing that torus. And then I'm going to fix the theorem afterwards. And I don't know why it's true, but it seems that it's customary in this subject to also call this thing H. And I'm going to try and use T all the time, but I might accidentally write down an H. And if I write down an H, H and T are the exact same thing. Yeah. Yeah, T is a maximal torus. And that means this is a maximal torus.
It's just that Bourbaki denoted tons of algebras by H, so that's.
Yeah, but I think. Okay.
For Henri.
I see. Good. Now I know. And then I want to study the flag variety, X, which is just the quotient of G by T. And now I want to state sort of my first theorem, which is a very old theorem. So I think that this one, the first bit was maybe 1950, 51, and I think that this bit's like 1957 or something like that. At some point, I'll stop remembering the dates. And this thing says the following. So the first thing that it says is that G equivariant line bundles on X are in bijection with co-characters of the torus. So in case, so this is just going to be homomorphisms of T and C star. Huh? Well, maybe they're all. But I'm going to need the G equivariant structure in a second, so it's important to me that. But yeah, I think it is all of them. I mean, that's true. It is true that it's all of them. But I'm going to want the fact that they're G equivariant. And so this construction goes as follows. If you have some character of your torus, then you can extend this to a map from the Borel using the fact that the Borel mod, its commutator, is the torus. And then you can just form sort of an associated principal bundle where this is the representation given by this character. So this is how you take a lambda, produce your co-character, and that's the only direction of the theorem that it'll give you. That's the first bit of the theorem. And then the second bit of the theorem is a little bit of a pain to state, or at least a little bit more so. So inside, so first I'm going to need a little bit of terminology. So inside of H, there is the root system. So let's say that. So let's say that this is SL3. And then inside of here, you have this. Sorry, let me make this page full. And you have the co-character lattice for your torus. And I'm going to take the normal picture that we talked about, and then I'm going to shift it by minus rho. This is equal to the half sum of the positive roots. And then for each guy, lambda, inside of here, we can define sort of an action of the Weil group on this guy, but it's shifted so that it's centered at minus rho instead of where it's normally shifted. So this new action is going to be the old action, except for you take a guy, you add rho to it, and you do the old action, you subtract rho. So just call it the dot, the star action. And to each guy, there'll be some unique element of the Weil group such that this is dominant. So there is one of these chambers which is picked out by your Borel. And then we say that something in this chamber is dominant, and the first bit is that for any lambda that's not on one of these walls, there is a unique element of the Weil group that takes you here, so that's called W. And then we say that if lambda is not on a wall, we say that it's right there. Okay, so that's sort of the first bit. And so their theorem says the following. So let lambda be dominant, let lambda with W star lambda dominant. Then the theorem says the following. It says that the cohomology of our line bundle is entirely concentrated in 1 degree, which is given by the length of this element of our Weil group. And this thing is going to be equal to the dual of the representation of I squared lambda. L is the length of the word in the Weil group. So you write it as like a minimal sum of transpositions.
That's the what's the
Oh, that should be this. Sorry. And then this is simple. I should be able to be called this finesse. I'll never call it again. Okay, so this is sort of the first theorem that I want to talk about. So then the other thing is that so maybe there are 2 other pieces. So if something is irregular, which means it lies on one of these walls, and there'll be no way of making it dominant, in which case all the cohomology will be 0. And then maybe the second thing that's about this theorem is that the dual to every simple row arises in this way. Okay, so that's sort of the first theorem that I wanted to talk about. But now I want to talk about...
And maybe we should say this actually answers Ron's question about equivariant versus arbitrary line bundle, because the flag variety doesn't depend on the group. It depends only on the type of the group. And so you're saying that for the co-characters of any maximal torus of any isogenous groups, you'll get G-equivariant bundles for the corresponding group. So in fact, all the line bundles on the flag variety will correspond to the co-characters of the, I can't tell now, either the semi-simple or the adjoint.
Yeah.
Right? And you're realizing the representations of the corresponding groups in the isogeny class for the corresponding line bundles which are equivariant for that group. That's what this theorem says.
So now let me talk about the generalization of this theorem, which is really the starting point of my talk. But it's kind of important to know about that theorem before I say this one. So that's the theorem of Valens and Bernstein from 1981. So let me define a little bit more notation. So let me define d pi. Let me define that to be the differential operators on the line bundle L lambda plus rho. So in particular, if you do d rho, that will be the ordinary sheaf of differential operators on X. And this is, if you remember, it's a sub-sheaf of the sheaf of C-linear endomorphisms of the structure sheaf of X. And then this thing is generated by multiplication by a function. That's going to give me an endomorphism. And then the other ones are going to be given by vector fields, where you can do differentiation of a function. Will also give me an endomorphism. It'll only be C-linear, it won't be linear over functions on X. And then you sort of have the following rule. If you try and commute, if you have a vector field in here and a function in here, and you compute these fields past one another, just get E times. No, so you just get the derivative of F in the direction of the vector field. Yeah.
On the lambda is diff L lambda plus rho, is it lambda plus rho or lambda
Oh,
minus
sorry,
rho?
this one should be, what am I doing?
That's a lambda.
Yeah. Sorry, I'm trying to put in the shift. So if this thing is, I guess what I mean, in order to make this work, I guess this thing needs to be chi minus rho. So this has to do with that picture that I drew a minute ago in the Borel-Bot theorem, where I had my hyperplanes shifted so that their origin would be a minus rho. Anyway, these rho shifts are like a really annoying part. Like, they're not really that important, but in order to be correct, we need to be sure that they're all there. Okay, and so let me define this guy. And then the first thing to notice is that G acts on X. Or actually, even better, it acts on L lambda, since I made sure that all of these things were, so let me call this thing chi minus rho, just to make it match. So G acts on L chi minus rho, since this was a G equivariant bundle. And so that means that by differentiating this action, we're going to get a map from the universal enveloping algebra of G into the global sections of the sheaf of differential operators. On that particular bundle. So that's maybe the first thing to notice, is that we have a map here. Okay, and so now I can start stating the pieces of the theorem. So part number one is that they compute a description of of the global sections of this ring of differential operators. And this thing is going to be the whole enveloping algebra. So it turns out that this is a surjection. That's the first bit of this theorem. Modulo the following ideal. So you're going to take the kernel of the map from the center of your universal enveloping algebra to the endomorphisms of the global sections of this one. Or actually, maybe I'll say the kernel algebra. And so, and let me just assume that lambda is better, so that this is regular. Okay. So then, so now let me say a little bit more about this. So by the last theorem, this thing is a simple representation. Right, the cohomology is non-trivial, only one degree, and it's the dual of a simple representation, which is just another different simple representation. And the center acts on any simple representation by a scalar. That's like Schur's law. And so that means that this is really going to factor through C. And now you can take the kernel of this thing, it'll be some maximal ideal in the center, and then you extend it to an ideal of the whole thing and then push it. So that's the first thing. So we'll call things that look like this central quotients. Of the universal enveloping algebra, and they're going to come up again. And then the other thing is that we'll call things that look like this, we'll call them central characters. Maybe I should have drawn this. Okay, so that's the first thing. And now the second thing is going to be kind of a souped up version of this part of the theorem here. Okay, so let me erase it, unfortunately. Let me just erase the top. So the first bit of the theorem is that now you have a map. Sorry, let me give this thing a name. Let me call this thing UG chi. The quotient.
So UG chi is gamma x dx d chi.
Sorry?
So it's just gamma x d chi.
Yeah, it's just a different name for the same thing, except for this is maybe if I'm thinking about it as an objective algebra and I didn't know anything about geometry, maybe I would define this thing based on how it acts on some representation. And then if I did know about geometry, I would define it this way. So then you get a pair of functors just from the existence of this thing. And the first one is just given by tensoring with d chi over u chi. Sometimes people call this localization based on like the case when you have like just some module and you want to turn it into an ordinary module and you want to turn it into a sheaf. So that's the first thing. And then the second one is just global sections. And these things are a pair of adjoint.
U chi is the same as G chi.
I don't think I ever wrote down a u chi.
Under the head.
Oh, I did. I'm sorry. Sorry. Yes. So there's this pair of functors. And the second thing is that this is an equivalence of abelian categories if chi is dominant and regular. So in this theorem, that should tell you that there was no cohomology. And that happens exactly when this guy lambda was already dominant, because then you can use the identity here, and then the length of the identity is 0. So that's where this dominant thing is coming from. And then the second thing is that it's a derived equivalence. If it's just regular. Not on the hyperplanes. So I drew a picture of it before, but yeah, you've got this hyperplane arrangement, it's centered here at minus rho, and then you might have some, sorry. So your lambdas, which were the chi minus rhos, would be like this, and then if I write it in terms of the chi coordinates, so this would be in lambda coordinates, and if I wrote it in chi coordinates, this would be at 0, and your chi would be here. That's why I did this stupid re-indexing thing, so that you have it centered at 0.
So regular just means highest weight is not fixed by the end of the divided.
Yeah. Yes. Okay. So this is sort of the main of the main theorem. And so in particular, what this means is that now to every single module over the enveloping algebra with this central character, I can really make it live on the flag variety. And then now I can start to like ask questions about its geometry. So now, sorry, just replacing what I had before. We don't want it in a second. Okay. So let me just show you one sort of thing that you can get out of having this localization theorem. And it's called the characteristic cycle. Okay, so the first thing that you should notice is that for a second I'm just going to specialize to when the character is rho. So I'm just going to specialize to diff. That everything will actually work the same for all the others. So this thing is filtered. By degree. In the vector fields. So basically to every, so this relationship is not homogeneous. So if you try and ask, so if you look at this relation, on this side, you've got one vector field and one function, so you might think that this thing has degree 1, but on this side you find that it's really just, that this thing is really just a function, so you have degree 0. So you can't put a grading on this thing using, by trying to count like how many tangent vectors, sorry, how many vector fields you need to write down in the element, but you do get a filtration. And so let me first try and compute what the associated graded. So the associated graded of this thing is, I claim, is going to be the symmetric algebra of the vector fields. Okay, so let me try and explain why that might be. It's just from exactly what I talked about a second ago. So if you look at this relation, this is all in degree 1. But if you look here, you would think that it's in degree 0. So when you take the associated graded of this relation, you only keep the highest degree part of it. And then you get the relation that V and F compute. And so now you have an algebra that's generated by vector fields and functions, except for they commute with one another. So this is just the definition of the symmetric algebra. Another way of thinking of this same thing is that this thing is pi star of the structure sheaf of the cotangent bundle of where pi is just the map from the cotangent bundle of x to x. So let me say why that is for a second. It's just that if you have a vector field, it's really a function on the cotangent bundle because you can evaluate it at each point. You could feed the vector to the covector and get a number. And so this is really just so things like that. So that's maybe the first thing. And so in particular, and in fact, this whole thing would have gone through for any d lambda. In fact, I could have made this thing. I could, sorry, there is pi. So I could have actually changed this. Not a word that would have changed. So in particular, if you have a filtered d-chi module, the associated graded is just, or has an action. Well, it used to have an action of d-chi, so now it's going to have an action of this. But this is just equivalent to saying that it is a coherent sheaf on the cotangent level. So let me give this module a name. So that means to M, so all of this stuff is just equivalent to saying that the associated gradient of M is a sheaf on. Okay, so maybe, and now through this composition, this means that actually to every representation of this ring I can get, if it's finitely generated, it turns out that I can find a filtration and then I can get some subset of the cotangent level. And this gives me some invariant of representations that we'll talk about in a second. Okay, so how much time did I spend? 45 minutes. Well, I started pretty late, but. All right. So now I'm able to, so now I've hit my theorem of the 80s. 35 minutes? Okay. Yeah, I mean, that's probably right. I started pretty late. Okay, but now let me hit my theorem of the 90s. But before I can, I need to define a certain subcategory here before I can say it. Actually, maybe this is a good time to say something else that was related to what I just finished saying. So the discussion of the characteristic cycle sort of implies that X is not really the right object to be thinking about. Because the characteristic cycle didn't live on X, it lived on T star X. And this sort of philosophy is kind of known as the micro-local viewpoint. And let me just sort of summarize like what it actually says. So it turns out one can promote d of x to a sheaf, d pi. It turns out that you can promote it to a sheaf on T star x. and lift, let me just call it dpi check, and lift all dpi modules. Check modules. And this is, in the future, this is going to be more of the perspective that I'm going to attempt to follow once we start talking about conical symplectic resolutions. This is maybe the first observation that wasn't sort of in sort of the old literature. But I just want to make this observation now.
Can we qualify it a little bit? So, when you define the characteristic cycle, you had to choose a filtration compatible with the action of the filter tree. And then there was some implicit statement that said that even though the coherent shift and the cotangent bundle depended on the filtration, the support of that shift counted with multiplicities does not depend on the filtration.
Yes.
So you get a well-defined cycle. Now, what you're saying is that you can actually quantize that shift by promoting it to a module over this shift of micro-differential operators. Will that depend again on the choice of a filtration, or is that going to be a functor between filter-derived categories? What exactly are you doing?
Yeah, so it will depend a little bit because of the
So it's not really a functor from the category of D modules to the category of micro-local sheaves, or micro-local D modules.
Yeah, I'm not saying that the characteristic cycle is the right thing. I'm just saying that you could maybe choose to always.
No,
yeah.
I'm asking, you're saying we can promote every D module to a D-chi cat module?
They have to be filtered.
Okay, so it's really a functor between the filtered categories.
Yeah.
Yeah, that's what I was asking.
Yeah, but yeah, you need a filtration in order to lift these things. Because without it, you have no idea sort of how to get into any coherent sheaf at all. And it'll be different because for these guys, when you set H to 0, you'll recover the associated graded of whatever filtration you put on there. So if you put on a different filtration, you would get a different H equals 0. But you could, if you invert H, then it really doesn't matter. But if you don't, so this thing, so sorry, what I'm trying to say is this thing is actually going to have, it's going to be some module over some formal power series algebra. And if you allow H to be set to 0, you would be able to detect the difference between different filtrations with an inverted H I wall. But so that's a really technical thing. Okay, so this is sort of the first thing. And now let me try and talk about the second theorem, which motivates the other thing. So the second major theorem is going to be about category O. So before I can define it, I need to tell you what category O is. So this is going to be some particularly nice category of representations of Okay, so the first, so O is going to be the collection of modules that satisfy the following two properties. So one, the center acts with a fixed, acts semi-simply. That's the first thing. So what I meant by that is earlier we talked about these central characters, which were homomorphisms from this thing to C. And so what I mean by this is that this is actually a direct sum, where on each piece of the direct sum, this thing acts by some fixed scalar, or sorry, by some fixed homomorphism to C. So that's the first thing that I want to say. And then the second thing that I want to say is that I want this thing to be locally finite. So I want the enveloping algebra of the Borel to act locally finitely. So let me say what that means, just in case. So what I mean is that for each x in M, the space UB times x should be finite dimensional as a vector space. Okay, and then the next thing that you can see is that by the discussion that I said earlier about what the center acting semi-simply meant, is that this thing actually breaks up into a bunch of pieces where I'm going to identify these homomorphisms from the center to C with the sort of guys I was defining earlier. So let me, the fact that this kind we're using chi again isn't an accidental. Let me have that before I say anything about that. So this thing is going to break up into a bunch of pieces, one for each central character. Okay, and then the other thing about this is that implicitly this thing actually depended on B. And nobody puts this here, but I'm going to, because it's going to be important for me later about the way in which this thing has a B dependence. Nobody ever does this. But I'm going to want to talk about changing B, so I'm going to put it on. So this thing depends on two parameters, the choice of your Borel containing your torus, and then it depends on this choice of a central character.
How does it depend on B? I mean,
If I chose a different,
the locally finite property is going to be preserved.
but I had a different B. No, it definitely won't be. It's going to depend on the direction of your Vermas. So let me say some examples of modules that are in here, and then it'll become totally obvious why it will depend.
By the way, when you say modules over UG, do you mean arbitrary vector spaces, locally compact vector spaces? What kind of modules are you looking at?
I mean arbitrary vector spaces, but let me just let them be finitely generated.
Oh,
Finitely generated as UG modules. But I'm not putting any topology.
Okay.
There's no topology on these things at all. I'm not doing some kind of something more complicated.
well, in the category O, you automatically get topology because you and that topology will depend on B, but will the category really depend on B?
Yeah. So let me tell you things in
Highest weights, lowest weights.
in category O. So let me consider a particular category O, where I consider the one for rho. So now maybe I should explain what I mean by this. So this chi is in H dual. And then there is a simple module of highest weight chi. It might not be finitely generated, but there's a simple module for each chi. I should say, let me say this a better way. So a better way of saying this is that there's a theorem. So this thing is in, these guys are in bijection with points back of the center. And there's a theorem of Harish-Chandra, which says that this thing is isomorphic to H1. H was T. So here, so this is where the Chi's lived. And I'm just taking equivalence classes. So maybe that's the right way to say it. So one thing that's in here.
The W action is the one that fixes 0 or where?
So in the Chi coordinates, it's the one that fixes 0. So this is not the highest, this is not the same as the highest weight. Basically, I've been using like lambdas to be highest weights and Chi's to be the row shifted. Yeah, so that's exactly what I was about to tell you right now. So the thing that I want to put in here is, one thing that's in here is the simple highest weight, 0. Or another thing that it would be is this thing is also global sections of the structure sheet. So I realize that. Okay, so that's one sort of guide that's in here.
Can I just write the relation between chi and lambda?
Yeah, so
Is it
chi
plus or
was
minus
equal
rho?
to, chi minus rho is,
Well, rho is it canonical or the square root of the canonical?
square root.
Rho is only the square root.
It's a half sum of the positive roots. Yeah, this is really annoying about this shift. Like, it's not something, yeah,
It's exactly the reverse of what you said previously.
No.
Action would fix chi equals rho or lambda equals 0.
it'll fix chi equals minus rho. Or sorry, it'll fix chi equals 0 and lambda equals minus rho.
Which is the opposite of what you said.
I think that I drew the picture at the very beginning with minus. So chi equals 0 is equivalent to lambda equals minus rho.
Chi equals rho is the structure sheet. That's what we said.
Yeah. Anyway, this is like very. Just believe me that I got these conventions right, or if I don't, just fix them later. It's not really that important. Like it's basically these row shifts kill everyone, and it's not that important. I mean, as long as you know which cat, as long as you know that I'm talking about this guy, it's not that important. Okay, so let me sort of say the things that are in here. So the other things that you have in here is you have all the simples that are contained whose highest weights are some W orbit of 0. This is with the ordinary, sorry, this should be with the star action, or another way of writing this. This would be the ordinary action on rho. These are two equivalent. And then the other things that are in here that are important are their Vermas. And so this is what I was trying to tell you, is that the direction of your Verma depends on V. Like which direction is highest depends on V, and so they'll be unbounded in some direction, and that direction depends on your choice of Borel. And so when you change the Borel, you change the direction to allow things to be unbounded in. So in the simplest example, if you were looking at SL2, then one choice of Borel, so let's say that this was zero, the simple highest weight 0, this is highest weight -2, and then this guy that we kept talking about, this minus rho, is right here. So this category will contain two simple objects, one of highest weight 0, one of highest weight -2, because the bile group just flips over this yellow guy. And then depending on your Borel, choice of Borel is a choice of orientation. So this thing corresponds to a choice of Borel. So this would correspond to if I chose this guy. And then if I would choose this direction, this thing would correspond. I'm sorry. To this guy. And then these vermas must be bounded in whatever direction I chose there. So one possibility would be that I have, so with my standard choice of Borel, then my vermas would be, they would need to be bounded in this direction. And so a verma might look something like this. But if I had chosen the other one, the verma would have gone in the other direction.
So yeah, I misunderstood what locally finite is. Locally finite doesn't mean that you have finitely many vermas, but it means that the filtration on the vermas is finite dimensional in the direction of your Borel.
Yeah, exactly. So basically for each guy that you choose in your verma, you act by B, would be moving you in one of these directions. So you have to stop eventually. So this thing is locally finite for this Borel. If I act with this element, it moves me in this direction, and eventually I'll stop. Like I'll run off the edge. Whereas if I was acting with the other Borel, I could keep going forever, and that would be locally finite. Okay. So these are maybe the two most interesting kinds of objects in here. And then I'll just mention that this thing has enough projectives and injectives. And their structure is very interesting, but I won't talk about it much now. Huh? Yeah. Actually, each of these individuals. So it turns out that the projectives in here have to break. Along the same symbol. Okay, so this is sort of an interesting category, and now I want to try and translate this into a more general form. So I want to try and ask the following question. What does being in category O mean geometrically? And so there's a theorem that it certainly appears in some work of Valenson, Ginsburg, and Sorgel. I mean, like it appears in a lot of people's work. I'm not exactly sure who to attribute it to. But there's a theorem that says that in particular, this guy, so you can localize it in order to get something that lives inside of your category of D modules. And so I want to try and identify the image. And it turns out that this thing is going to coincide with the category of n equivariant. Where n is the unipotent radical of B. So it's the strictly upper triangular stuff.
It's just true for rho, not for any chi?
So let me tell you the theorem. So once you put things into it depends on what kind of equivalence you want to mean. So if you want an abelian equivalence, then this is true for any dominant chi. They're dominant and regular chi. That was basically going to be, it's going to follow just from the valence and Bernstein thing. But if you have one that is just regular, then you need a derived equivalence, which is which already appeared in the valence.
But it's still the same statement. It says that this piece of the category O is the n-equivariant twisted D-modules.
Yeah, that's right, but it's just what kind of an equivalence.
But it's a derived, just a derived.
Yeah. I'll talk a lot more about like exactly when you can tell things are the same, or sorry, exactly how you deduce these kind of statements in a second once I set up the general framework. But yeah, so you get something like this. And then the other bit is that this is actually a property, not a structure. Turns out that there's not any independence. If it can be made n equivariant, there's only one way to do it. All right, so that's the first thing. And then the second thing that you can figure out is that if you have some module in here, then the character, so let me just tell you sort of a fact. So X can be written as double cosets, like this. So you can write it in terms of its n orbits. These things are called Schubert cells. So let me give this thing a name. And then the theorem is, one is that you can actually find the filtration. I won't mention that part. But once you find the filtration on any element here, then you can see that the characteristic cycle is actually going to end up being just a direct sum of the conormal bundles, closures to the conormal bundles of these Schubert cells. And these are just some numbers. I'm sorry. So let me say this again. So you take your D module. So you take your representation. You turn it into a D module. Then you use this trick that I told you about in order to turn it into a sheaf on the cotangent bundle of X. And then you just take the sort of the class of that sheaf, like take the components of its support with like a certain weight. And the component, and if you take the support, basically it's just going to be a disjoint union of conormals and Schubert cells. That's what I'm saying.
What were the coefficients?
They're just some numbers. I didn't tell you what they are. Oh, you mean like what kind of number?
Integers?
Integers.
Are they?
I mean, yeah, I think they'll be positive for a module, right?
Yeah, by definition positive for a module.
This is not homologically equivalent. This is equal to. This is actually quite equivalence of the cycles.
Yeah, this is
Not the chart.
yeah, it's just
So
some
that's what cycles.
Yeah, I haven't put any equivalence relation of these things. Yes, so all I'm doing is I'm just looking at the multiplicity of each component. It's always a positive number. Positive, or sorry, non-negative measure. Natural.
Coefficient of some invariance of the modular.
Yeah, they're just some invariants. I'm not saying anything about their structure, except for that you have just one for each Schubert cell. One thing that is not true is simple modules are not just a single Schubert cell. Like that's like a very hard example. The first example where that happens is like an SL4 or something like that. But basically, representation theory would have been easy if, when I took the characteristic cycle of a simple, I just got a single Schubert cell.
Is this the kind of looseness theorem?
Yeah. Okay, so now let me maybe. I think that this is maybe enough now that I can give the general definition. So I had a theorem I was going to state, but I think that maybe I should push it off till next time, and instead I should give you the definition of a conical symplectic resolution and category O for such a thing. Because it's just a direct generalization of this example. Like now that you've seen this example, it's extremely easy to give the general definition. Okay, so the first thing that you need is the definition of a symplectic cone. So symplectic cone of weight n is an affine Poisson variety, and it's usually singular. With a C star action satisfying some properties. So in the future, I'm going to need a lot of C star actions, so I'm going to give each of my C stars a name. And this one I'm going to call C star R. And the reason is, if you know physics, it's the R symmetry. Or it'll end up being the action of the R symmetry. It needs to satisfy the following properties. So one, the regular locus needs to be a symplectic leaf. So let me say really briefly what. Huh? So sorry, I meant to give my name. Yeah, thanks. Okay, so let me say just a word about like what a symplectic leaf is. So if you have a Poisson variety, it means it has just means that its functions have a Poisson bracket. And given a function then on a Poisson variety, you can use the bracket to turn it into a vector field. Basically just by bracketing with that function. It'll be a derivation and it's a vector field. And then you can solve the ODE given by that vector field at any given point, and you can flow along that integral curve to other points. And symplectic leaves are the equivalence classes of this equation. So like if you look at all functions and all differential equations and all, starting at any point, you ask all the places that can flow under any, under the vector field determined by any function. If you look at all the places it can flow, that'll give you it'll break your manifold up into pieces. Those pieces are called the symplectic leaves. And I'm saying that the smooth part of this thing needs to be a symplectic leaf. So that means that almost everywhere you should be able to, for these points, you should be able to float any of the points.
So it's really the same because it's very Right.
Yeah, that's another way of saying it, yeah. And then the other part is that you need this thing to contract your cone to a single fixed point. So let me maybe give you a more algebraic way of saying that. So this is equivalent to the following two more algebraic statements. So the first one is that the weights of your action on the functions are non-negative. And then the second bit is that the only functions of weight 0, or the invariant functions, is a way of saying it, are the only ones that are constants. So anyway, these two statements are equivalent to this statement. So this action, so like what you should think of is that as you let this parameter go to 0, it should suck everything of your variety down to a single fixed point. And then finally, the third one is a compatibility between these two structures, and it's pretty easy. It's just that the Poisson bracket is homogeneous of degree minus n. Okay, so now let me
You don't want to define a non-affine line.
they're all going to be they're all going to be affine for what I care about. Basically, the affine here is going to correspond to the valence and Bernstein theorem holding later. So I had some theorem about how differential operators on the flag variety were determined by their global sections, like those categories were equivalent. One way of saying that is that the flag variety is d-affine, it's affine for differential operators. And that's going to be a consequence of the existence of some affine cone that I haven't mentioned yet. So the affine...
So in the Bernstein story, the symplectic cone will be the Nilpotent cone?
Yeah, I was going to say that in a second. Let me give one other definition. Yeah, and so now this is the part. So then the second definition is we say that M0, which is one of these symplectic cones, we say that a resolution of a symplectic cone is conical symplectic if the following things hold. So one, the symplectic form on M on the regular locus extends to 1 on N. And actually, well, I'll say something about this in a second. And then the C star action extends to M in such a way that I is C star R at the variant. Okay. So let me just make a small note about this. So it's trivial that the omega on the regular locus, this is my symplectic form, extends to a 2 form. On that. Like that, like so In fact, I think even the closed is obvious as well. So that part of the definition of symplectic is trivial. Or sorry, of a symplectic resolution is trivial. The force is that it might be degenerate. By that I mean it might just give a Poisson structure. It might not actually have full rank everywhere. So like just being able to extend your closed two form from the singular locus over the entire thing, that's trivial just by, or that's not very hard. But the force of this definition is knowing that it's not degenerate.
So what makes it work? How does it doesn't apply? Because in A you have dimension, you could have dimension 1, but then this dimension is backward. So what makes
So
it
I'm not sure that you can have dimension one.
Don't waste time if it's not obvious.
Basically, like I'm not sure that the Poisson doesn't rule out codimension one, but you might. But this point is that the form might be degenerate. Like that'll let you extend it to a closed two form. Bartog's would let you do that, but it wouldn't tell you.
No, I didn't see how about
I think that you do know that it will be regular, at least to codimension two. It's like I think that's. I don't remember the proof off the top of my head, but I think that's not. I think that was something that Clay, so we showed, and it wasn't like it's not a hard theorem. I can look it up, but I think that you almost have this for free, but this part is hard.
what was the name you just
Collated.
Okay.
But let me just like punt on whether or not, I'm pretty sure that that's true, but let me punt on that. Let me say something that I'm sure is true. So you may be able to show, so if you were able to show this,
If you're collating.
well, yeah. But suppose that you were able to show this, you're not done. You still need to show that. And this part is like what gives, like basically things that just allow it to extend versus things that allow it to extend and be non-degenerate, like behave in very different ways. Like the forces here is all I'm trying to say. All right. So now let me tell you how we fit our example. So in our example, we were studying the cotangent bundle to the flag variety. And it turns out that that there's a very famous resolution where the image, the resolution, this is called the nilpotent cone. Another way of saying it is that it's cut out by the vanishing of all of the invariant functions. So it's the functions on this. You take your functions on G dual, and you cut out by all of the invariant functions of the But for like SLN, or like this is just matrices that are nilpotent normally in this sense. These are the coefficients of your characteristic polynomial. That should be a plus for positive. So you don't kill the zero function, which is certainly invariant, or the constant functions, which is certainly invariant. You only kill the ones with positive degree. So that's just a plus. So what I'm saying is that if you were, in the case that you were studying SLN, then this ideal would be spanned by the coefficients of the functions that take a matrix and get you the coefficients of the corresponding characteristic polynomial. And this thing it turns out it's a symplectic resolution. Or conical symplectic resolution, CSR. Okay, so now I'm almost maybe ready to get to a stopping point. So let me just say a few words. Okay, well actually, maybe I'll ask you guys to tell me what you would prefer. So I can either give you other examples of conical symplectic resolutions, or I could tell you how to define category O for a conical symplectic resolution. And so, which would you prefer?
What's the time frame?
I'd like it to be, well, let's see, where are we now? It's about 6,
Now,
or sorry, it's about 5:55.
maybe we should talk about your plans for
Yeah. Okay.
future talks.
Sure. Yeah, okay, so maybe here will be so here are sort of the things that I would like to talk about. So one is I need to give a talk where I build, where I talk about the properties of category O for a conical symplectic resolution. So the kind of things that would need to go in here is sort of that it's a highest weight category, it carries 2 actions, categorical actions, grade group, let's see. Things that maybe would be interesting to do here. Explain what Puzzle duality, well, sorry, yeah, maybe it would be actually, so this would maybe be one thing that needs to be done. The second is actually give the definition of what a symplectic duality is, given that I've done this. But like a totally different tack, which would have some overlap with this, but would maybe be very different, would be talk about Coulomb branches. So the sort of thing that I would like to talk about here is that I mentioned that the Coulomb branch didn't have a definition until extremely recently. And so there's the definition that's due to Braverman, Finkelberg, and Nakajima, which identifies this with the GK equivariant homology of a version of the convolution Grassmann. So it's basically something like P, the G bundle on the disk, 2 disks union together over the origin. So I've heard people call this space the ravioli, or the raviolo, or the UFO space. Together, so if I just had this, this would be the convolution Grassmannian. Together with a section of some associated vector bundle, where R is some G-val. So I could start trying to talk about exactly what their definition of the Coulomb branch is. And then from this, you can try and construct so you can try and construct graphs of the deformed branch. So this is just one section. And so then the sort of things that come up in this, there would be various things about sort of outline Springer fibers, vortex moduli spaces. So these are basically something like you can get maps from P1 into the Higgs branch, and then you take some activation. Turns out that this will have an action of the quantized electronic So anyway, so these are sort of the kind of things that I can talk about. So it's sort of up to like what you would think is the most interesting. I'd really like to talk about this stuff, but I think that like it's basically impossible to talk about it without actually having an example of what a category O looks like, and like what the structure of category O is, and like basically everything that I would be doing here would be entirely unmotivated. So I really think that maybe the best thing is to go into the deep structure of category O for at least for a little while. So this is what I'll definitely do next time. And probably this as well.
So when would that be next week?
Or Thursday, it's up to you. People come on Thursday.
Count.
Yeah, it's a huge talk.
Okay, well then next week then.
The cage talk is at 3 to 4:30, right?
So that's not conflict.
Yeah, but whether you want to visit two talks, maybe you should turn that off and then we'll discuss. I mean,